Observational astronomy. The main source of information about celestial bodies and other objects is visible light, or more generally electromagnetic radiation. Observational astronomy may be categorized according to the corresponding region of the electromagnetic spectrum on which the observations are made. Some parts of the spectrum can be observed from the Earth's surface, while other parts are only observable from either high altitudes or outside the Earth's atmosphere. Radio astronomy. Radio astronomy uses radiation with wavelengths greater than approximately 1 mm, outside the visible range. Radio astronomy is different from most other forms of observational astronomy in that the observed radio waves can be treated as waves rather than as discrete photons. Hence, it is relatively easier to measure both the amplitude and phase of radio waves, whereas this is not as easily done at shorter wavelengths. Although some radio waves are emitted directly by astronomical objects, a product of thermal emission, most of the radio emission that is observed is the result of synchrotron radiation, which is produced when electrons orbit magnetic fields. Additionally, a number of spectral lines produced by interstellar gas, notably the hydrogen spectral line at 21 cm, are observable at radio wavelengths. A wide variety of other objects are observable at radio wavelengths, including supernovae, interstellar gas, pulsars, and active galactic nuclei. Infrared astronomy. Infrared astronomy is founded on the detection and analysis of infrared radiation, wavelengths longer than red light and outside the range of our vision. The infrared spectrum is useful for studying objects that are too cold to radiate visible light, such as planets, circumstellar disks, or nebulae whose light is blocked by dust. The longer wavelengths of infrared can penetrate clouds of dust that block visible light, allowing the observation of young stars embedded in molecular clouds and the cores of galaxies. Observations from the Wide Field Infrared Survey Explorer (WISE) have been particularly effective at unveiling numerous galactic protostars and their host star clusters. 4950. With the exception of infrared wavelengths close to visible light, such radiation is heavily absorbed by the atmosphere, or masked, as the atmosphere itself produces significant infrared emission. Consequently, infrared observatories have to be located in high, dry places on Earth or in space. Some molecules radiate strongly in the infrared. This allows the study of the chemistry of space. More specifically, it can detect water in comets. 52. Optical astronomy. Modern images are made using digital detectors, particularly using charge-coupled devices (CCDs), and recorded on modern medium. Although visible light itself extends from approximately 4000 A to 7000 A, 400 nanometers to 700 nanometers, that same equipment can be used to observe some near-ultraviolet and near-infrared radiation. Ultraviolet astronomy. Ultraviolet astronomy employs ultraviolet wavelengths between approximately 100 and 3200 A, 10 to 320 nanometers. Light at those wavelengths is absorbed by the Earth's atmosphere, requiring observations at these wavelengths to be performed from the upper atmosphere or from space. Ultraviolet astronomy is best suited to the study of thermal radiation and spectral emission lines from hot blue stars (OB) stars that are very bright in this wave band. This includes the blue stars in other galaxies, which have been the targets of several ultraviolet surveys. Other objects commonly observed in ultraviolet light include planetary nebulae, supernova remnants, and active galactic nuclei. However, as ultraviolet light is easily absorbed by interstellar dust, an adjustment of ultraviolet measurements is necessary. X-ray astronomy. X-ray astronomy uses X-ray wavelengths. Typically, X-ray radiation is produced by synchrotron emission, the result of electrons orbiting magnetic field lines, thermal emission from thin gases above 107.10 million kelvins, and thermal emission from thick gases above 107 Kelvin. 47. Since X-rays are absorbed by the Earth's atmosphere, all X-ray observations must be performed from high-altitude balloons, rockets, or X-ray astronomy satellites. Notable X-ray sources include X-ray binaries, pulsars, supernova remnants, elliptical galaxies, clusters of galaxies, and active galactic nuclei. Gamma-ray astronomy. Gamma-ray astronomy. Gamma-ray astronomy observes astronomical objects at the shortest wavelengths of the electromagnetic spectrum. Gamma rays may be observed directly by satellites such as the Compton Gamma Ray Observatory or by specialized telescopes called atmospheric Cherenkov telescopes. The Cherenkov telescopes do not detect the gamma rays directly but instead detect the flashes of visible light produced when gamma rays are absorbed by the Earth's atmosphere. Most gamma ray emitting sources are actually gamma ray bursts, objects which only produce gamma radiation for a few milliseconds to thousands of seconds before fading away. Only 10% of gamma-ray sources are non-transient sources. These steady gamma-ray emitters include pulsars, neutron stars, and black hole candidates such as active galactic nuclei.